Hey, welcome back everyone. Hopefully you all had a good weekend. The last time we talked a little bit about stochastic optimization. So basically this is a continuation of the optimization algorithms part of the course. So with stochastic optimization, instead of computing the gradient, which is actually the summation of the gradient of the loss corresponding to each data point. So instead of summing over all of them, we're just gonna pick a random subset of terms in the summation to approximate the gradient. And we have shown that this is actually an unbiased estimate of the gradient. In fact, in machine learning, because the data size is very large, a lot of the times at least, whenever somebody says something like gradient descent, they really mean stochastic gradient descent, actually mini batch gradient descent, for example. And we also looked at other variations of stochastic optimization. For example, approximating the gradient using mini batches in Adam, Adagrad, and so on. And these methods work very well for first order optimization methods and less well for second order methods. And then we ended the lecture notes on optimization by looking at some very simple hyperparameter tips. Again, your mileage may vary. It really depends on the model, the application, and so on. And then for the second part of the last lecture, we started to talk about neural networks. We motivated neural networks by talking about learnable features. The idea was that we can always replace the input x with some feature. And previously, we replaced x with a fixed feature. With neural networks, we're going to replace that with a learnable feature. And then in the learnable feature, the input is still going to be x again. So then we can, again, replace x in there with another learnable feature. So then we have many layers of these learnable features. And that led to the simplest type of neural network, which is the multi-layer perceptron. We also went over a bit of terminology. So today we're going to go really deep into neural networks. So continuing from last time, this is, so basically our output, predicted output, is going to be some weights times a learnable feature. And the learnable feature is given by psi, a function psi of some weights times another learnable feature, hl minus 1, and so on. All the way down to whenever we're tired of everything, tired of so many layers, then we say, okay, h1 equals psi of w0x, and we leave it at that. So now when we learn the model, we have to learn, when we learn the model parameters, we're really learning wl, wl minus 1, and so on, all the way down to w0. And this function can be written more compactly. So y hat equals wl psi of yl minus 1, psi of w minus 2, and so on, all the way down to psi of w0x. Again, this is called a multi-layer perceptron. Okay, so then we kind of dug a little deeper into all the mathematical notation. So in machine learning, we usually like to write things in vector form because everything is a vector, everything is high dimensional. Okay, so then we kind of started with linear regression and we expanded things out a little bit, just to make sure that we have a vector output instead of the scalar output in linear regression. So this is where we're going to start today. Just going to go over things a bit more slowly to make sure that you guys understand every little detail about neural networks. Okay, so actually this is good. We have the multi-layer perceptron model that I wrote down last time. So let's copy that. Okay, that didn't work. Give me another. Let me try again. Okay, so this is where we'll start. Okay, so let's begin over here. So here we have h1 equals psi of w0x. So what exactly does that look like? Well, x equals to x1, x2, all the way down to x minus 1, and usually we say the last element is just going to be a 1. So then w0 must be, therefore, it's going to be a matrix multiplying this vector to give us another vector, right? So for w1, it's a matrix, and it has the same number of columns as the number of components of x. So we can write w as w11. You can kind of see that the notation will get very ugly. So that's why we don't really write things down in matrix form all the time. So let me just give the w an index 0 for the first, the 0 corresponds to this 0 over here. So w11, okay, w12, okay, all the way to w1 n0, where the n0 is the same as the number of components of the previous previous feature. In this case, we're just starting from the very beginning. The previous feature is just x, so this actually goes all the way up to n minus 1. Okay, so now that's why we have commas here. Okay, and then at the end we have a b0. Okay, so that's the first row, and the second row is going to be the same thing. So w21, w22, all the way to w2 n minus 1, and then we have b2. And this keeps going, and eventually we have so now how many rows do we have, right? So this whole thing needs to equal h1, and h1 is basically going to be sorry, this is actually, so not h1 yet, but we like to call this z1. So before we apply the function psi, we call that z1. So this is going to be z. Again, the indices are getting quite confusing, so I'm going to put a 1 here. Yeah, maybe it helps to use a different color. So this index 1, index 0, index 0, index 1. So the indices, kind of the outer index, is going to be in red. And the inner index will be the standard green color. So it's going to be Z1, Z2. Well, how many Zs are there? That depends on how many rows of W we have, and we get to choose that. Because this, remember, H is just going to be a learnable feature, and then I guess we get to pick the dimensions of the features. So it's going to be Z all the way to Z n Z1, Z2, all the way to Zn2, actually Zn1 minus 1. And then the last component by convention, we're going to use 0 for that. So all of this is has an index of 1 on the outside, so those should be in red. Okay. So now if we come back to W, so now we know how many rows there are. It should actually be N1. Actually, I made a mistake at the end here. Just 1 second. Yeah, so here be N1 minus 1. And then here, so the first index goes from 1, 2, all the way to n1 actually, because we still have a 1 sorry, let me go back a little bit. There's actually the 1 comes later. Okay, so we don't need the 1 for now. The 1 will come when we use the function psi. But this is still going to be w, so basically there's n1 minus 1 rows. Okay, so you'll be glad that we do everything in vector form. But we should do this once. So let's keep track of all the indices. So the 1 index in red, so those indices are for the outside. Okay. So that's basically starting from the beginning. We're not going to go all the way, but I just wanted to show you, just write it out slowly once. Okay, so that gives us the z. So now h1 is going to be psi of z. z1, yep. And then that actually equals to, so h, so h is going to be h1, 1, h2, all the way down to hn1 minus 1, and then there's a 1 at the end. So that's where the 1 comes in. And this, just component by component, this is going to be, so now we apply the activation function g of the first component, z1, and then just activation function g of the second component, z2, and so on, all the way to g. So here notice that g has no index. It's the same g, same function g. We apply it to each component of z. Okay, and then the last component, this is just going to be a 1. Okay, so that gets us from x to h1, right? And then just to emphasize the outside indices, so that should be red. Okay, so this is an outside index, and then all of these are also in red. Okay, so then you can kind of see, you keep going. So now the h looks like the x before, except that it's h, right? And then there could be a different number of components in h. So then you would then multiply h by the next w, w1, and that will give you z2. And z2 will look something like this, except the red index is going to be 2. And there could be, again, a different number of components. And then you would apply the psi function again to z2. So that's going to be applying g to all the components of z2. And then appending a 1. That will finally give you h2. And this process keeps going until you get all the way to y. Right? So that's basically what the slide is trying to show here. All right, so we start with x, we append a 1 at the end, and then in each layer we have a W matrix whose last column is going to be the biases, and then we have the W part, the weights part, that multiplies our input feature, which will always look like something like this with a 1 at the end. After we multiply W with x or h, we're going to get the z variables. So that's going to be everything happening inside the psi function. So after we get the z variables, then we apply the psi function, which is just going to be applying the activation function to each component and then appending a 1. Okay, so hopefully that gives you a kind of a better idea of how everything works, and be glad that we're going to do this once, and then from now on is vector form. But keep in the back of your mind that like there's no magic here. Vector form is just a shorthand for all this ugly ugly matrices for which we don't really want to write down every term. So the W's are the weights. On the slides, I'm actually not showing the kind of the all the indices just because it gets very cluttered, but you can see the indices in the written notes. Okay, and the B's are called the biases. G's are the activation functions. Okay, so let's move on. So some terminology. We already went over this last time. So we have the different layers. Layers refer to the vectors, y and all the h's as well as x. Y is the output layer, h is the hidden layer, and x is the input layer. The z's are called pre-activations. Z's are basically the w times h. That gives us z. So pre-activation because we only multiplied by w. We haven't applied psi. So pre-activations. Okay, and then h, that's why h is also called the post-activations because we get h after applying psi. And as we talked about previously, h is also called the features, right? These are the learnable features which motivated the multi-layer perceptron architecture. Okay, so now drilling down further. So we talked about what all these vectors are called. The elements of these vectors are known as neurons or units. And then we can talk about input unit or input neuron for x, hidden for h, and then output for y. And this whole structure can be interpreted as a network. We start with the input, and then after the input goes through some weights, we get the next layer h. This layer gets manipulated according to the next layer of weights, and then we get our next hidden layer. Within each layer, what happens? So here is from a different textbook. So the A's are the same as our H's. So these A's are basically the same as our H's. So the H goes into one of these bubbles. They get multiplied together with some weights. So that's what these arrows are saying. It's a matrix multiplication. So that means basically involving multiplying and summing a lot of things. The three here, each bubble is actually just one unit. And the row of bubbles together will give us the layer, right? So within one unit, we're looking at one component of H. Each component of H involves the previous entire H inner product with one of the rows. Let me just make sure, yeah, one of the rows of W. So then we have a sum, and then after the summation, we apply the activation function, and then we get our next H. We basically get our next one component of the next H. So that's basically this unit. The other unit here is giving us a different component of H. And then this entire layer then goes through the same thing again to the next layer of units. Okay, so anyway, there's nothing new here in the picture. All of it is in the math, but this could be one way of interpreting what's happening. So now, looking at a higher level, we have the input, which goes through, which are the input units. So this is the input layer. The input layers goes through some weights. So for example, if you look at the entire input layer and all of the arrows connecting the entire input layer to this unit, we can see that This is actually the activation function. So we do an inner product with the weights, pass through the activation function, and then that gives us one component of the one unit in the next layer. Okay, and this keeps happening for all the components. So now these outputs are going to be combined together again with the next layer of weights to give us, and then pass through some activation to get a component of the output in this case. So here we have two hidden layers. Okay. So we talked about everything. So hopefully everything should be clear based on this slide. The only thing we haven't really talked about is what is G. So G is usually a fixed function called the activation function, and we usually apply the same G in for every unit and across every layer as well. Again, there's no rule saying that we have to do this, but this is typical. Okay, so some common choices of G, the activation functions. So sigmoid. So this is what a sigmoid looks like. Basically, if you input any value from negative infinity to infinity, all of those values get squashed down to a value between 0 and 1. Another common choice is hyperbolic tangent. So similar idea, except that you squash everything to between -1 and 1 instead of 0 and 1. Soft plus, which is log of 1 plus exponential of z. So this basically looks like a smoothed angle here. Everything negative will get mapped to 0 almost, and then it smoothly transitions to a linear function. And probably the most common nowadays is the rectified linear unit, or ReLU. And this function is basically g of z equals max of 0 comma z. So if the input is less than 0, then the 0 would be the bigger of the two. So then the result would be 0. So if you input something less than 0, you get 0. If you input something greater than or equal to 0, then the maximum between 0 and that input will be that input. So then you just get a linear function with slope 1. So sometimes one may wonder, okay, what about the linear activation function? Turns out that this is not a common choice. Like, you might use it for one layer. Maybe there might be one layer for which you don't want a nonlinear mapping. But usually we don't use it across many layers. So why is that? So to see this, let's do a bit of math again. Okay, so I guess it's always helpful to write down our model. So okay, let's not use red. Let me go back to green. So we have y hat equals to WLHL. And then HL equals to psi of, okay, psi of WL minus 1, HL minus 1, and so on. I guess, so I'm going to do it a little bit more simply over here on the written notes, and then I'm not going to explicitly write down the row of ones. So I won't be writing down the biases, but if you have biases, it's basically the same thing. So we'll see that on the slides later. So in general, we have HL plus 1 equals to psi of WLHL all the way down to H1 equals psi of W0 X. So I'm just ignoring the ones and the biases just to keep the writing a bit simpler. Okay, so now if g of z equals z, so if we're using a linear activation function, that means that all the psi's, basically we can erase them because the mapping is identity, right? So we simply pass whatever is inside psi right through to h. So now we would have, so I guess we can work backwards. Now we have h1 equals w0x, h2 equals w1 h1, again no psi, right? So then we can now write down we can now replace h1 with what we have over here, w0x. And if you have a bias, so do we want to do the bias? If we do a bias, then basically there will be a one. This would be basically, we basically do x. We can basically assume that the bias is hidden inside w, right? That's what we have been doing. And then there will be a 1 inside x. And then every h would have a 1 as the last component. And then the matrix will include the biases. So I guess what we're doing here is pretty general as well. Okay, anyway, let's continue. So that's h2. And then h3, hopefully you get the idea. h3 is going to be w2 h2, which is equal to, we can substitute in h2, which is h1 w1 w0 x. Okay, so you can kind of see that, you can kind of see the pattern, and eventually we'll get hl equals wl minus 1, hl minus 1, and following the pattern we should get wl minus 1, wl minus 2, a big product of matrices all the way down to w0 times x. And then finally y hat equals to, it's just going to be a one more w multiplied, wl minus 1 all the way down to w0x. But then this whole thing, we could just multiply the matrices first, and then we just get a gigantic W. So then this is basically just going to give us a linear map. So then, yeah, so then now it just turns out to be like a linear regression model, right? So maybe I put a tilde on here. So now it's back to linear regression, right? So then if we pick the activation function to be the identity function or even a linear function, then we just basically end up going back to linear regression. We're basically not getting any, not getting a function that is non-linear in the parameters. All the layers can be collapsed down to one layer. So that's why we use non-linear activation functions. And the activation functions are known as the non-linearity. So this on the slides here, I've written explicitly the ones and also the biases, but the idea is the same. If you multiply everything out carefully, you can try this as an exercise. You will get the same term that we had, a bunch of w's multiplying x, and then plus a bunch of bias terms, b plus w, wb terms. All of these are kind of, they don't really interact with x, but again, these are just a bunch of vectors, and they will add up into some overall vector. We're still going to lose the point of having all these layers because all these vectors can be collapsed down into a single vector. Okay, in the end, we just get back this y hat equals wx plus b. So not non-linear, basically. Okay. So hopefully you can follow that. So let's summarize a little bit. So we have our model, which is y hat equals a nonlinear f of x the parameters of our model are going to be the WLs, so all the weights of every layer. And explicitly written, this is equal to WL psi of WL minus 1, psi of WL minus 2, finally psi of W0x. These are the parameters we would like to learn. And to learn these parameters, we basically need to define a loss function. And the common, I guess one common loss function is just a multiple output regression loss. So we can just say, okay, let's take a look at our data. The data labels are yi. We're going to subtract from that yi hat, our model prediction, and then we take the 2 norms squared for each data point, and then we add this up across every data point. So this is something that we saw from the multiple output linear regression slide. The difference here is that we're not doing linear regression anymore, so the y hat is now going to be replaced with our nonlinear model, the multi-layer perceptron network, over here. With linear regression, we had a closed form formula for W, but now we don't. So now we have to basically use these iterative optimization algorithms that we talked about last week. Okay, so we're going to be talking about how to do that. Well, actually, the concept is very simple. We just have to compute the gradient of L. And then if we're using gradient descent, for example, we basically update the W's by having a random guess W initially, subtract some step size times the gradient with respect to W. The only issue here is that the W's are they occur in many places, and this function is very, very nested. So then this could be a little bit complicated. So we're going to talk about that in a bit, but first let's motivate why we want to use this model, right? So the previous motivation was that we wanted to have basically linear map, so W times a learnable feature. And the learnable feature involves W times a learnable feature and so on, nested many times. So why do we want this? Well, that was one motivation, but there's also a theoretical motivation as well. So this is the universal function approximation of the multi-layer perceptron. So what it says is that if you have a function here in red, so if you have a continuous function which is on a closed and bounded set. So let's consider, for example, we're just going to consider the range, the domain being somewhere from here to around here. So this is a continuous function on a closed and bounded set. A multi-layer perceptron with one hidden layer and sufficiently many hidden units on that layer can approximate this function to any arbitrary precision for most choices of activation functions. So that is basically depicted by the blue approximation. So the blue approximation is actually a multi-layer perceptron. So you can see that we can approximate this region very well, right? If we had more, we can even expand the blue function to approximate any other region as well, as long as the region we're considering is bounded. So now for the asterisk for activation functions. So the activation functions must be nonlinear, bounded, non-decreasing, and continuous. So nonlinear, bounded, non-decreasing, and continuous. So this is basically what we have for all of these common activation functions over here. Okay, and because of this property, neural networks are called universal function approximators. Okay, so we're actually going to show this next. We're going to start with a very simple example. Let's just consider the ReLU activation function. Okay, so probably you should do this a bit slowly. Okay, so ReLU, rectified linear unit. So we have g of x, well, let's use Z because we always call Z. We always use the letter Z to denote the pre-activations. Okay, so what does that look like? So we can draw this. So that should just looks like 0 on the left. And then Z. So this is G of Z. So now we can actually move the function left and right a little bit. So for example, if you want to move the function left a little bit, let's say by 1/2, then we will have a function that looks like this. So this would be G of Z plus 1/2. Right, so hopefully you remember from high school when you replace the variable with the variable plus something, that's a translation to the left. If you don't remember, the easy way to see this is that previously I can plug in something into G to get this green result, right? So now, if I want to get the same green result, I need to plug in something that is 1/2 bigger than what I plugged in over here, right? So if the Z over here is 1/2 bigger, so 1/2 smaller, sorry, then I would add 1/2 to it, and then I would get the same result as the green curve. Okay, so hopefully you can follow that, but that's from high school. Okay. So so again, you can also do, for example, if I do inside the argument, I can do Z minus 1/2. If I do Z minus 1/2, then the function will be translated to the right by 1/2. So this is the blue line. And now I can also multiply it by a -1, and then I will get this function, which is G of Z minus 1/2 minus that. Okay, so so bear with me here. I just want to construct a bunch of different variations of G, and then we're going to be adding them up and see what we get. Okay, so now I'm going to draw another graph. So now we can take the green and the blue curve. We're going to subtract them. If we take red minus blue, on the left here, before the 1/2, minus 1/2, sorry. And then this is 1/2. On the left, we have 0 minus 0, so that gives us 0. In the middle region, between minus 1/2 and 1/2, we have the red, which is a 45-degree line. Subtract 0. So that's going to give us a 45-degree line. And everything above this, we're going to take the red one and subtract the blue line. For any increase in the value of the red, we have the same amount of decrease in the value of the blue function. So they're going to cancel out, and then we get a flat line over here. So this one is actually G of Z 1 plus 1, G of Z plus 1/2 minus G of Z minus 1/2. Okay. So that's basically what the slide is showing, right? So we have the value, we can slide it to the left, we can slide it to the right, and then kind of negate it. So then it goes down, and then when we subtract them, we get kind of this pattern over here. Okay, so now we're going to use this function as a staging area, I guess a staging point to construct more variations. Okay, so let's go back to the written notes. Okay, so I'm gonna copy this graph so we can see it. be a bit smaller. Actually, we need it to be a bit bigger. Okay, bigger. Okay, so yeah, sorry, just not very good at using this. Maybe a little too big. So let's do it like this. Okay, we're gonna just extend the y-axis down a little bit. So what we can do is we can take this function and we can add a constant. If we add a constant at the end, we'll be shifting the function up and down. So for example, we could shift it down and then it will look like this. So this function is going to be g of z plus 1/2 minus g of z minus 1/2 plus some constant a, right? In this case, the constant a is negative. So that's up and down shift. We can again shift the function left and right as well. So we could shift the function left and then we will get something like this. Yes, just definitely not good at drawing. Right, we'll get a function, the blue function like this. And this blue function would be g of z. Remember when we shift left, it's going to be it's going to be replacing z with z minus some constant. So minus a negative constant in this case, right? But if b is positive, then we will be shifting right. Yeah, so that should be a minus because we're taking this function, this entire function, and then replacing all the z's inside with z minus b. So that's how we shift functions. Minus, okay, minus g of z minus b minus 1/2. Okay, so that's what we have on this slide. So we took this function and then we can shift it up and down and left and right. So now I'm going to continue working with this function. The other thing we can do is to replace the z in this function with a constant times z. And that is going to either shrink or stretch the function horizontally. So I'm kind of running out of colors. Yeah, let me get a different color. So for example, let me draw the function first. So let's say we have this function. Now, instead of going up and down between 0, minus 1/2 and 1/2, we can go up and down in a smaller region. And in addition, we can flip the function left and right. So this is basically taking this function and replacing the z with some constant. In this case, because we're shrinking and also flipping left and right, the constant, it would be a negative constant. And then the constant, the absolute value of that constant is actually greater than 1. So then you will get this magenta line. Okay, and lastly, we can also change, so let's go back to here. So we know that if we do plus 1/2 over here, minus 1/2, we get an increase from -1/2 to 1/2. So that's this part. And the 1/2, -1/2 and 1/2, they're coming from the left side where the red and the blue curves, they go up and down at -1/2 and 1/2. So that's where the 1/2 came from. But we can always change the 1/2 to some other number. And then if we change the 1/2 to some other number, then the region of increase and decrease will be different. So that's another thing we can do. So now finally, I'm gonna choose yet another color. And that will give us a function that looks something like this. So okay, so it turns out that this function doesn't go all the way up as much because the amount that we go up depends on how close the red and blue functions are. If we have a narrower range, then the function will only go up in this narrow range, and then when the blue function starts going down, the difference between the red and blue will start to be flat, right? So this last function doesn't necessarily go all the way up to up as high as before. So the purple one is going to be g of z plus 1 over 2d. If d is greater than 1, then basically we'll start increasing a bit. The region of increase will be a bit narrower in the middle. Okay, so now we have so many different variations of this function. And that's what this slide is trying to show. So first you can flip horizontally. You can change the slope here. Over here on the right side, we keep the same slope, but then we change the region of increase, and also we can change how much we increase. So these are all the options we have to play around with this function. The whole point is that by using a combination of these, by changing the slope, changing the region, and also changing the position horizontally and also vertically, we can construct a very little segment of a straight line with arbitrary slope and at an arbitrary place on the graph. So that's basically what the left animation is showing. It should be an animation. Let me see. Okay. Yeah. Can I? Okay, there we go. I think it's playing. So by choosing the right parameters of this function up here, we can create a little piece that is matching locally the red function. So let's do that again. So previously we had many different variations based on a single parameter like B, like D. So A, B, C, D. So A, B, C, D are the things we can do to this black function individually. On the slides, we're doing them all at once. And if you do them all at once, you can always have a little piece of the blue function that matches really well with the red function. Right, so let's just look at that again. Okay, so now imagine you add up all of these little pieces. So for example, yeah, maybe we can just draw this out one more time. Don't think I have sufficient animations. Okay, so just one last step here. So we had this red function. We try to draw it similar to the slides. Excuse me. By choosing the right parameters A, B, C, and D, we can approximate any little segment of the red function really well. Of course, our function over here, using all the parameters A, B, C, D, they will always have a horizontal line before and after this little piece. So for example, we can have this little piece, and we can also have another little piece over here, let's say, right? We could have these two functions. Okay, that's supposed to be horizontal. So now we can actually add these two functions up. Okay, if we add these two functions up, initially we'll have these two parts. We'll be adding these two parts up, so it will be a constant, like that. When we get to the part where purple is increasing, the gray function will increase at the same slope as the purple part. And when we get to the part that blue is increasing, the purple part is no longer increasing, so there's no contribution to the slope from the purple. And then we'll start increasing based on the blue function, something like this. Okay, and then we keep on going straight. And we can always bring down this gray function by adding a constant to it. And that will give us the black function, which is going to be, that's not the right place. Okay, there we go. Can bring it down to the purple function, and then as soon as the purple is increasing, we're going to track the red function very closely until we track, and then all the way through the blue part, and then it's going to follow the blue horizontal line. So right now we've only shown two different functions added together, the blue one and the purple one. But you can imagine you could have many different functions added together. And then together, they're going to track the entire red curve really well. When you add the functions up, the slopes will match, but then the constant part of the functions will give us a gray curve that will be too high, but we can always bring the gray curve down to where the red function is by adding a constant. So that's the idea. So that's basically what the right side is showing. We have everything on the left added together. That's going to give us the gray function that we drew, which is really high up. That's the summation part. We're summing over I for a bunch of these g functions. So g of ci z minus bi plus 1 over 2d. We can even have a common d because we just choose d to be pretty large. The larger the d is, the smaller we can make this part. So the smaller piece of the red function we would approximate for each of the terms of the summation. After we add them all up, we get a gray function, which is too high up. And then we add alpha, which is the term that brings the entire gray function down to the blue function that you see over here. Okay, so this basically shows that if we start with ReLU, we do some transformations of the ReLU, and then we get this piece. We can do various transformation of this piece to get the little pieces on the left plot that you guys saw. And then by adding up all these little pieces, and then bringing the entire value down or up, depending on what we need, we can always approximate part of the red function arbitrarily well. Right? Arbitrarily well because we can always pick a D that is really large and then adding more pieces. And then you will have better and better approximations. So this shows that we are able to approximate the red function really well. But the next thing we need to show is that this function, which can approximate the red function well, this function is actually a multi-layer perceptron. So we're going to show that next after a 10-minute break. Okay, welcome back. So let's continue. So now we're going to show that this function is actually a multi-layer perceptron. Okay, so that's basically what this slide is saying. So basically all we have to do is to write this function in the form of a multi-layer perceptron. If we can do that, that means that a multi-layer perceptron would be able to approximate any function on a bounded set arbitrarily well. Okay, so let's do that. So in this case, the multi-layer perceptron only has one hidden layer. So what does that look like from the definition of the multi-layer perceptron? So basically we would have, so let's take a look. We would just have y equals wh, and then h would equal to psi of w0x. So that's what it would look like, right? So let's write that down. Okay, so one layer multi-layer perceptron looks like w0, sorry, w1 psi of w0x, right? So that's what it looks like. And in our case, it turns out that I'll write down the answer first, and then we can expand everything to show that we do get the previous function that we had. So it turns out that we're going to get a bunch of ones and minus ones. Many of these. And then we're going to have a summation over all the AIs plus alpha for the last component. So this is basically our W1. And then we're going to have, so remember that our psi function, remember that the psi function, after we apply it, we basically append a 1 at the end. So, okay, so, but let's start from the inside. So here we have C1, B minus B1 C1 plus 1 over 2D. And then we're going to repeat this again, but then with a minus. And then we move on to index number 2. So then we have C2 minus B2 C2 plus 2D, 1 over 2D. And then the same thing minus 2D. We keep going until we get all the way down to Cn minus Bn. So this is 2 columns. So the first column is C1, C1, C2, C2s, all the way to Cn, Cn. Second column is going to be a bunch of minus Bc plus 1 over 2d. So minus Bn, Cn plus 1 over 2d. And then another one, Cn, and then minus Cn, minus Bn, Cn, minus 1 over 2d. Okay, so we have that. And then we're going to take this whole thing. So this is a 2n by 2 matrix. We're going to multiply that by x and 1. Okay, so then after that, we're going to apply the activation function or the psi function to this entire thing, and then append the 1 at the end. Okay, so I needed more room over here. So let's take a look at the dimensions. So this matrix is 2n by 2. After we multiply by a vector of size size 2, a column vector of 2 elements, we're going to get a long vector here with 2n elements. Right, so this whole thing inside the psi function will be 2n elements. Okay, so maybe this psi should be a g. Let me double check this. Normally the g is the activation function, so you apply the activation function g, and then you append a 1, and that gives you psi of w0x. Okay, and then this part is x, right? We just append 1 to the x, and then this part is supposed to be our w0. It's a matrix. Okay, so that's basically, I'm saying that this function, this multi-layer perceptron with one hidden layer is actually the same function that we saw earlier. Okay, so let's just multiply everything out and see this. Okay, so let's work on one part at a time. So let's look at w times w0 times x. Okay, so let's make some room. w0 times x will give us a vector, and then the vector will be c1. So we take this c1x and then multiply plus minus b1 c1 plus 2d. So that's this part times 1. Okay, sorry, I forgot the x. So next we take c1 x plus minus b1 c1 minus 1 over 2d. Okay, and we keep going. In the end, we'll just get the last term. I'll just do the last term, cn x plus minus bn cn minus 1 over 2d. Okay. So we can simplify it a little bit just to collect some like terms. So here we have c1x minus b1c1. So this is the same thing as c1 x minus b1 plus the last term 1 over 2d. And then c1 x minus b1 minus 1 over 2d, and so on until we get to cn x minus bn minus 1 over 2d. Okay, so that's what wx is. So now we're gonna go out a little bit and apply the function g to each component. So then g of w0x will just be applying g to each component, right? So basically this is just copying what we had. So let's just copy. Sorry. The bracket a little bit to make some room. And then we apply g to each term. And then this psi of W0x will just be so this is element wise, right? Element. Okay, so the psi of W0x will be the same as yeah, it will be the same as G, except that we have a 1 at the end. So again, no need to write everything again. The only thing we need to do is to make room for the 1 down here. So now we're ready to multiply psi of W0x with W1. So we can see that the W1 is just 1 minus 1, 1 minus 1, 1 minus 1, and so on. All of those 1s and minus 1s will get multiplied by, in pairs, by the G's corresponding to CI's. The first one has a plus 1 over 2D. Second one has a minus 1 over 2D. And then the 1 at the end gets multiplied by the summation of AI's plus alpha. So hopefully you can see the pattern. So let's finally write down what y hat is. Okay, so now back to y hat equals W1 times psi of W0x. And that's going to be equal to G of C1 x minus B1 plus 1 over 2D. And then, so that's the 1 multiplying this part. And then we take minus 1 multiplying this part. So minus G of C1, G of C1 times x minus B1 minus 1 over 2D. Okay, and then this pattern will continue because next we have a 1 and a minus 1 that will go with C2, go with everything the same thing as above, but then with index 2. Okay, so just writing that down quickly. Hopefully I don't make a mistake. Okay, I just did, but this should be a minus. Okay, so you keep going. And then eventually you have G of Cn x minus Bn plus, so that's the second last term, so this term over here, and then we get to the last one finally. Okay, so now we have taken care of all the terms involving G. And then the last term is going to be a lot of these alpha i's, sorry, a lot of the all the AI's added together plus alpha. So it's going to be A1 plus A2 plus until AN, and then finally plus alpha. Okay, so hopefully you see that this is exactly the same as the function f that we had, because we can always move this a1. Let's see if I can do this properly. Over here, we can move this a2 over here, right? And then so the an goes over here. And now the other a's are going to be in here, in the middle part. So then we don't need this part. And then in the end we have the plus alpha. The alpha, remember, is shifting the gray function. Shifting this gray function down, that's what the alpha is doing. Right? So now this is exactly what we want. Summation. Actually, let's just we don't need to write this down. Let's go back to the slides. So now we have this so this should be a G here. So it's really going to be, yeah, so G applied component-wise to this, the result of this matrix multiplying this vector. So that means that this function, which is basically a bunch of these little segments added together, which can arbitrarily, which can approximate the red function arbitrarily well. This is really just a single hidden layer, multi-layer perceptron. So this basically shows that, this basically shows the result that we want, which is that, again, any continuous function on a closed and bounded set. So let's say this set, we can approximate that function using a multi-layer perceptron with one hidden layer and sufficiently many hidden units on that layer. Okay, and for most choices of activation functions, so the one we have seen is the ReLU activation function. Okay. Again, a lot of ugly math, but we need to see this once so that you guys know, kind of know deeply what exactly we mean by universal function approximation. Okay, so now we can move on to talk about training neural networks. So remember we said that the parameters they're kind of nested inside this nested psi functions. But in any case, we still need to take the gradient with respect to all of them. So what we can do is we can collect all the weights, all the W matrices together, and then we can call them theta. And then we can compute the gradient of our loss function with respect to all of these different weights, theta. And then we can use something like gradient descent. And that's pretty simple. I mean, the high-level concept is pretty simple. You can use gradient descent, you can use AdaGrad, Adam, any of the previous iterative optimization algorithms that we looked at last time. The only thing is, how do you compute this? How do you compute the gradient? So because the neural network, at least the multi-layer, actually all neural networks, but in this case, we're talking about the multi-layer perceptron. We have a bunch of nested functions. If we have a bunch of nested functions, we need to use a chain rule in order to get, for example, the gradient of L with respect to, let's say, the innermost W over here. So we need to use a chain rule. Okay, not here yet. Chain rule. So the multivariate chain rule. So here we have, so now going back to more basic math. So if we have a function u, which is a function of v and w, but then v and w are also functions of x and y, and everything is differentiable, then if suppose we want to take the derivative of u with respect to x, then we basically have to take the partial derivative of u with respect to each of v and w. So that's here and here. And then multiply each of those derivatives with the derivative of v with respect to x, and then w with respect to x. So that's the multivariate chain rule. Applying this chain rule to what we to training neural networks, what we want is to take the partial derivative of L with respect to one of the matrices or any of the matrices WL. So that's going to be the same as derivative of our loss. Let's just use the square loss. Okay, again, we can move the derivative inside the sum, so not going to write this down again. And then when we do that, the 2 comes down, and then we should have some arrows on these y's. Okay, so let's not worry about the arrows. We're gonna be looking at all the components very carefully in the next few slides. Okay, and then finally, after we take the derivative of the outside function, which is a square function, we need to take the derivative of the variable remaining with respect to the variable that we want to take the derivative of, WL. Okay, so I think we've seen this already. Previously, this part was easy because we have a linear model, but now this part is kind of hard. It's a neural network. Okay, so before we actually get into the neural network differentiation, let's talk about a general algorithm for efficiently computing derivatives or gradients. So this algorithm is called backpropagation. So we'll be using backpropagation to take the gradient of neural networks, but we're going to see it for simpler examples first. So let's just say that x is just a 4-dimensional vector. And then we define a function y, which equals to x1 plus x2 times together, and then x1 plus x2 multiplied by x3 plus x4. And we would like to compute the partial derivatives of the output with respect to the input variables x1 to x4. So how would you normally do this? So let's just quickly review the multivariate chain rule, right? So this is just direct application of multivariate chain rule. So we have y equals x1, x2, x3 plus x4. But let's make y a format that is closer to the multivariate chain rule. So y equals z1, z2, z1 equals x1 plus x2, z2 equals x3 plus x4. So for example, if we want to do partial y, partial x1, we have to first differentiate with respect to each of the variables that y directly depends on. So that's going to be partial y, partial z1, and partial y, partial z2. And then multiplying each of these, we need to take the partial derivative of z1 finally with respect to the input, x1. Okay, so that's how we do it. So this part is going to be 1. That's a 1. Sorry, this is a z1, z2. And partial y, partial z2 is equal to z1. Partial z1, partial x1 will be 1 from here. And then this is 0. So eventually we just get z2, which is equal to x3 plus x4. Okay. And then we can, of course, do the same thing with respect to x2. Okay, and then it's going to be exactly the same procedure. Okay, just let me double check this. Okay, so that seems correct. Now, what if you do it with respect to x2? Okay, yes, it should be correct. Okay, so back to the slides. So that's basically what we did, applying the chain rule for multivariate for multiple variables, and then you can get one of the partial derivatives. We can now differentiate with respect to x2. It's the same procedure, except that now z1 and z2 must be differentiated with respect to x2 instead. In this case, it's going to be the same thing. Okay, so actually, it would actually help to write this down just for you guys to see why backpropagation later on will be useful. Okay, so So right now we're not doing backpropagation. So this is supposed to be a little slow. Again, the direct dependencies of y. We need the partial derivatives of these, and then we need to differentiate z1 with respect to x2, and then z2 with respect to x2. And this part is z2, this part is 1, this part is z1, this part is 0. So then we get the answer is z2, which is also x3 plus x4. Okay, so maybe you already see that we're wasting some effort here because we ended up computing this part. We're repeating this computation. We're also repeating this one, right? These two are fine. But we did repeat some computations when we do this. And now if we keep going and we want to say partial y partial x3, that's going to be equal to, so we're not going to do this in full, but just to show the repeated computations that we end up doing. So now again, I'm not gonna keep writing this, but this is the formula for it. We need to evaluate this one, this one, this one, and this one, and then we can get a result pretty quickly, right? But the last one, we'll see that here is gonna be partial y, partial z1 again. So now this is gonna be repeated. This computation will be repeated if we continue to do it by hand. This part is fine, x4. And then next we have partial y, partial z2. Again, we already did that here, so now we're repeating it over here. And then this part is fine, right? So we're repeating, we have some repeated computations, which is why the normal way of simply what's called the forward mode differentiation, the naive approach, is not so efficient because we're repeating some of these computations. Okay. So we ended up performing 4 additions because in the end we have to add x3 plus x4, and then we add x3 plus x4 again. This is a repeated computation, and then x1 plus x2, and then x1 plus x2. So that was not the most efficient way. So the idea of backpropagation is to make sure that we don't waste our efforts repeating all of these computations. So how does that work? So what backpropagation does is going to compute partial y partial z1 and partial y partial z2 right away. And then it's going to save these results. After saving this result for the first layer of partial derivatives, it's then going to go down another layer to differentiate with respect to the input. So now we have the partial derivatives with respect to all of the inputs, x1, x2, x3, x4. Again, using the multivariate chain rule, so this looks like a sea of letters, but here we have so here is where the repeated calculation was previously. Right, and then these ones are partial derivative of z with respect to x in the end. So because we save these results, we can easily now evaluate all of these. We only need to perform 2 additions because z1 plus z2, we already calculated them. Sorry, z1 and z2, we already calculated them. So as soon as we know what the result is z2, well, we're gonna load in the result over here. And then for the second calculation, we know that the result will be z2. So then we're gonna load in our calculation over here. We don't need to repeat these calculations. So now we're able to save some additions. For the small example, obviously this seems pretty trivial. We can just do it the normal way and there would be no problem, but But if you go back to the multi-layer perceptron, you will see that, well, we're going to do a lot of chain rule here. There could be many, many layers. Each layer could have a big matrix, W. We have many, many weights, many, many different partial derivatives. So that will make the computation much more expensive. And not only that, computing the gradient, which involves all of those different components of W, will only give us one update iteration. After we do this update, we're going to be computing the gradient again. Why? Well, because every iteration, we're going to be plugging in a different set of parameters. When we plug in a different set of parameters, the gradient will be different. So basically, in our very simple example, that's basically saying we're going to evaluate every time we do an update iteration, all the z's will be different, all the x's will be different. So the gradient, the value of the gradient will be different. So we basically have many, many parameters that we need the gradient with respect to. And then we also need to take the gradient many, many times. So we need all the computational savings that we can get. Okay, so let's see. So that's basically what backpropagation is. It's a very simple idea. But let's expand things a little bit into a computational graph. So on a previous example, we had y1 equals, y equals z1, z2, where z1 is x1 plus x2, z2 equals x3 plus x4. So we can represent the function as a computational graph like this. So we have x1 plus x2 gives us z1, x3 plus x4 added together gives us z2, and then those multiplied together gives us y. So each node and operator is represented as each variable, including the intermediate variables and the operations, are represented as a node. And backpropagation involves two steps. First, the forward pass. We're going to plug in the value, the input values into the nodes, and then we're going to compute all the intermediate values all the way to the output. And then the backward pass is computing all the partial derivatives with respect to each variable. And then we're going to do that starting from the end. So first, in our previous example, we first computed y, derivative of y with respect to z1 and z2 first, making use of the stored values from the forward pass. And then we can compute the derivative of z1 with respect to x1 and x2, again making use of the stored intermediate values from the forward pass. So that's the overall how backpropagation works. So let's put this to practice using a different example. So here, let's consider a slightly more complicated example with three variables. F of x, y, z equals to log of x plus y squared plus z. So this function can be represented as a slightly more complex computational graph. We have the input x, y, z, add them together, add x and y, we get x, y. We go through the square operation that gives us x plus y squared. So I'm kind of highlighting in blue what the operation is applied to. So this squared operation is applied to x plus y. And then the addition operation is applied to this thing plus z. Right, so that gives us the inside here. And finally, we log the entire thing. And that gives us the output. So now if we apply backpropagation and we want to compute all the partial derivatives with respect to x, y, and z, so this is basically the gradient of f with respect to the input, we do it backwards. We start by taking the gradient of this with respect to this. So is log something? So because it's log, well, the derivative of log is just 1 over the inside. So we just take 1 over whatever the inside is. And then we keep that around. Next, we're going to take the gradient of this with respect to this. Well, this is just going to be the blue part plus z, right? So the gradient will just be 1. And it's going to be, overall, if we go all the way from the end to here, the gradient will just be 1 times what we had before. So that's using the chain rule. So every time when we go back one step, we keep what we had previously, and then we take the derivative from the next stage and multiply by that. Okay, so in this case, the derivative is 1 because this expression differentiated with respect to this expression, that's just going to be a simple 1. Okay, so now we go back again, and we keep the previous result, and then we multiply by the derivative at this stage. And that's just going to be the squared function. The derivative of the squared function is going to be 2 times whatever is inside. So that's why we have a 2 plus xy here. And finally, we go all the way back to x. Well, the derivative of x plus y with respect to x is just 1. So we multiplied that with what we had previously. And now we can do it for y as well. Again, the derivative of this with respect to this is 1. And then finally the z, we can also get that easily. So now we need to take the derivative of this expression with respect to z. So that's just going to be a 1. And then we multiply by everything we had afterwards. So that's backpropagation. In reality, of course, we'll be plugging in some values of x, y, and z. So here we did not do the forward pass because we didn't really plug things in. But now we're going to do the forward pass. So basically we're going to do another example where we're going to take the gradient with respect to the input, evaluate it at 2, 1, 1. Just picking some arbitrary numbers. So x equals 2, y equals 1, z equals to 1. So the first step is the forward pass. So this is the forward pass. We plug in 2, 1, 1. Add things together, get 3, square that, get 9, and then add 9 and 1, you get 10 over here, and then log 10 is about 2.3. Okay, I'm not sure if that's actually correct, but okay, that may not be correct, so we'll fix this later. I think 2.3, yeah, that's definitely not correct. Okay, so but it's going to be some number over here. Okay, so now first step we take so now we have done the forward pass. So now doing the backward pass. We take the gradient of this with respect to this. So all we're doing is taking all that is going to be 1 over this. That's the log. But what is this? Well, this thing, we already stored the value of it is going to be 10. So this is just going to be 1 over 10. We keep that value around as we go back again. So now gradient of this expression with respect to x plus y squared, that will give us 1 times what we had before. Okay, in this case, we did not have to plug in this value, right? Previously, we plugged in this value, which was convenient that we stored it. Here, it just so happens that the gradient is always 1, so we didn't need to plug the 9 in. Okay, but we multiply the new part with what we had previously. Okay, so that gives us 1/10. We keep that around. So now, going back one more, the squared function derivative is just going to be 2 times the inside. What is the inside? That's going to be 3 because we stored that value. So then, okay, plug that in. 2 times 3 times 1/10. That's 3 over 5. Okay, now going back again. So now we keep what we had before, multiply by the new part, which is 1. And then overall, the gradient is going to be 3 over 5. So now we have, by going back, we have computed partial f, partial x evaluated at 2, 1, 1. And we can, so that's 3 over 5, and we can do the other partial derivatives very easily because we have already kept all of these intermediate partial derivatives along the way. So for y, we already kept the 3 over 5 over here. So now we just have to multiply the derivative of x plus y with respect to y. That's 1. Multiply that with 3 over 5. Okay, and then for z, from this step over here, we get a 1 for the derivative, and then multiply by what we had before, 1 over 10. So hopefully that gives you a very clear idea, a concrete idea of what backpropagation is. And the backpropagation can work on any function and is especially useful when you have many nested functions. For example, here we have a log of some other function which involves a square, right? So this is one more layer of nesting compared to the z1, z2 example over here. And we can see that despite the many layers, we did that by hand very quickly. So that's a good sign. So the next thing we're going to do is to apply this to the neural network. And then we're going to work out all the math by using the backpropagation algorithm. So again, we're going to start with the forward pass, evaluating, so plugging in our input and then evaluating all the intermediate variables like Z1, which is W0X. And then we apply activation to get H1. And then we get Z2, H2, Z3, H3, and so on, all the way up to Y. So that's the forward pass. Afterwards, okay, so all the way to Y. Afterwards, we're going to be doing the backward pass. We want to have the gradient with respect to all the different W's, including even the first layer. Right? And then we're going to be applying a bunch of chain rules, so no time for that today. We're going to work out all the details with applying the chain rule on the network, neural network, and then eventually we'll be able to derive the expressions for all the different derivatives. Okay, so that's all for today. So I think the important thing today is to understand what backpropagation is, not necessarily apply to neural networks, but apply to any computational graph. So next time we'll do the same thing for neural networks. So see you guys next time.